In this screencast, I want to talk about data integrity. So what does data integrity mean? Well, for a large organization, it means that the data that it stores reflects the real world. It's consistent and correct in terms of it reflects exactly what's going on in the real world. The relational model provides rules and constraints that help to maintain this correctness and consistency. Some of these rules are structural rules, which means that they're defined universally by the relational model, namely that they're built in to the model in some sense. Other rules flow from the application-specific things that are specific to a given organization. And these are things like domain constraints. In other words, the values that different things can take on that represent what's going on in the world. The SQL language and tools includes tools to define both kinds of these rules. The first type of rule I want to talk about are domain constraints, namely that the values that a data element may contain are limited to a certain set of values. This is similar to the concept of a data type that you've probably run into in many of your computer science courses. Namely, all the values in a column, in other words, all the values that a variable can take on, must be taken from the same domain. A simple domain might be you've got a list of allowed values for some attribute, say order status, and you might store that as a string, and it must be one of the values pending, meaning you're waiting to do the order, shipped, canceled, or returned. And also many things like numbers will be limited to specific values, like you might only care about positive integers. The next kind of constraint is the primary key constraint, and this is referred to as entity integrity. And remember, each tuple in a relation has to be unique in some sense. You can't have any duplicates. So every relation must have a primary key. What that means is that there's going to be some attribute or set of attributes that define the tuple uniquely. In other words, you can use, if you know the values of those attributes, you know the complete tuple. So for an example, below here, the primary key is emp ID, and we've got these different example rows here, different tuples, and we can see that there's a problem. There's duplicates down here, so that certainly can't be allowed because you can't have, if it's going to be a unique identifier, you certainly can't have the same identifier point to two separate employees, and nor can it be null because otherwise this employee is not identified, this row is not identified by the emp ID. Right now I'm going to go through these pretty quickly. We'll spend a lot more time in class and on some examples until they're become second nature to you. So what's referential integrity? What's a referential integrity constraint? Well, that's a foreign key, basically, and what it does, the integrity constraint, is that that foreign key value must match a primary key value in some relation, or it must be null. So in other words, the foreign key either has to point to a tuple that's uniquely identified by the value of the foreign key, or perhaps not point to any value at all in the other table. So in this example, we've got a set of employees and we've got a set of departments. The employee information is in one table and the department information is in another table. So given those two relations, the employee table has a primary key of emp ID. The department table has a primary key of department ID, and we're going to have a department ID also in our employee table, and we're going to hope we want that to be our foreign key. But we've got a problem because this value for department ID is not contained in the tuples of the department table. Notice it is allowed, though, to have a null here. That just means that Susan Martin here has not yet been assigned to a department. It could mean that. It could mean other things. That's one of the issues with null, and we'll spend a lot of time on null later in the term. Here's another example for foreign keys. We've got three tables, a product table, a PC table, and a laptop table. They all happen to have the same primary key. Products are uniquely identified by their model number, presumably, and the PCs also have a model number that will be a primary key for them, and the laptops will have a different product number. There seems to be some convention here going on, although it's not specified, that laptops begin with a 2 and PCs begin with a 1. So, at any rate, the interesting thing about this particular example is, notice that the primary key model in PC is also a foreign key into the table for product. And similarly for laptop. So you've got your primary key in a table that's also playing the role as a foreign key. Circling back a bit, on this slide I want to emphasize that the primary key is a semantic thing, typically, in any instantiation of the relational model, in any relational database, that reflects the semantics of the organization. So here, I mentioned this on the last slide, but here, obviously, model number is going to be unique across the entire organization for the different products, so that it can identify the information about each product and can be used, if you will, as an index into the table that contains the information about the products. Similarly, same thing for PCs and laptops. This is obviously going to be, since it's unique for all products, it's going to be unique for PCs and unique for laptops. Now, some of these constraints are, you can think of them as algebraic constraints. Now, what does that mean? That means you can define them using the relational algebra. And we'll go through that. This will largely become transparent and not all that relevant as we go along. But initially, it says from a theoretical perspective what kinds of constraints can be expressed using the relational algebra itself. And remember, but when I say the words relational algebra, I mean the operations and the data types that belong in the relational model, namely tables, tuples, selection, projection, join, etc. So we're going to talk briefly now on the next few slides about entity integrity, and then referential integrity, and then finally some domain constraints. We'll talk about assertions later on in the course. So I want to start with the foreign key and how we express that constraint algebraically. It happens to be one of the sort of the most natural ones to think about. Because if you think about what a foreign key has to be, so it's some attribute in a table, and it has to have a value that's in the primary key, an attribute that's a primary key in another table. So what does that mean? Well, that means if you take the projection onto the foreign key, okay, so you just look at that column that contains the foreign keys in the relation R, then that has to be a subset of the primary keys in relation S. Or equivalently, what does it mean? It means, so think about what does this mean if you sort of quickly drew the Venn diagram. It means this set contains this set. In other words, it's bigger. So if I take R and subtract off this bigger set, what am I left with? I'm left with the empty set. So both of these are two equivalent ways of expressing the constraint that a foreign key must satisfy. Primary key is a little more difficult to express. Remember, what it means is it has to be unique across all the tuples. So you can't have any duplicates of the primary key, just like you can't have two duplicates of the tuple. And if two tuples are to agree on the primary attribute, then obviously it has to agree on all the other attributes. And since the tuples form a set, then that would mean that you can only have one of those tuples. So how can I express this? I can express this by taking the relation R and taking its cross product with itself and keeping them, identifying them separately, R is R1 and R2, using the rename operator. Then what can I do? I can check to see if the keys agree across the cross product in the two different components. And I can also check if for those tuples they disagree on a non-key. And obviously, since it's supposed to be a primary key, you want that to be unable to happen. In other words, if the keys agree, then it can't be possible for a non-key to disagree. The same non-key here as in here. And what you end up with is that if you've got primary key, then that must be equal to the empty set. So we can express this algebraically. This is just a restatement of what we got up here, a little more carefully done. This says that the primary key in relation R1 is equal to the primary key in relation R2. That's this. And the non-key attribute in relation 1, comparing it with the same non-key attribute in relation 2, they basically cannot be, if they're not equal to each other, then you've got a problem. So basically this is saying that for any non-key attributes, if they disagree, then wouldn't have the empty set, and so that they must agree since you ended up with the empty set. So that takes care of primary keys and foreign keys. Now let's look at the following constraints that would be value constraints, basically. Let's go back to our simple product PC laptop example here that we've been working with in the screencast. And let's suppose we wanted to express that the speed of every PC sold must have a numeric value between 1 and 3.5. So how would you express that? Think about that question, and also think about how you might express that laptops with 16 gigabyte of RAM or more must have a price greater than 500. So let's look at the first one here. We can look down in the PC table and we can see that we've got speed expressed. And so as you've been practicing, you know that you can now do a selection on here and check to see which one of these things satisfy that. And similarly for the second one, we've got a table for our laptops. You can look in that table and see if it satisfies this. So now take a few seconds, stop this screencast and see if you can write down the selection operator and a Boolean expression which will allow you to check whether these different constraints are satisfied. So for the first constraint, we wanted every PC sold to have a speed between 1 and 3.5. That, in other words, you can rephrase that to say that no PCs are sold. You'd have a numeric value less than 1 or bigger than 3.5. And so that's pretty easy to express here. We've got an OR, so we're going to select out anything with a speed bigger than 3.5 or a speed less than 1.0. If that happens, we know we violated this constraint. So in order to impose this constraint, we want this to always be equal to the empty set. Similarly for the laptops, right? A laptop with 16 gigabyte of RAM must have a price greater than 500. So we flip that around for the 500 price of 500. So if the RAM is bigger than 16 and the price is less than $500, well, we have a problem. So this constraint saying that for the RAM to be bigger than 16 and the price to be less than 500, there must be no laptops that satisfy that Boolean expression. This has been a quick introduction to data integrity in the relational model. In our next class, we'll begin talking about SQL, and you'll see how SQL is used to define tables in a relational database, and how we use it to impose these sorts of constraints to make the relational database that we may be developing reflect the real world of the organization in which it will exist.